Hello students, in this video I'm going to show you how to do the example Cobb-Douglas production function that I had on this last slide for our calculus review PowerPoint. So I'm giving you this Cobb-Douglas production function where the quantity of output is a function of the amount of capital and labor the firm has hired. Remember that number out front is just what's called a technology coefficient. Kind of just talks about how productive the capital and labor are. That can go up or go down if the productivity falls or increases. Notice the powers. This is the alpha power and the beta power. These are always going to be numbers that are just bigger than 0. And notice both of them are to that 1/2 power at this point. So we are to find the partial derivative of the production function with respect to capital and with respect to labor. So what each of these partial derivatives will tell us is how productive one more unit would be if we added one more unit of capital and one more unit of labor. All right, so let's go ahead and start doing these partial derivatives. Remember when we go to find the partial derivative, you kind of use this different notation for the D part. What you're doing here is you're going to hold labor constant. So the idea is I'm going to add one more unit of capital, but I'm going to hold my labor constant at whatever level it is. So for example, if I currently have 25 workers, the L to the 0.5 power, 25 to the 1/2 power is 5. I literally just would keep it a 5, okay? So I'm not going to change the L to the 1/2 at all, but I am going to treat the K to the 1/2 as a variable. So notice that variable is multiplied by 400, and it's multiplied by whatever number that is, the L to the 1/2 power. So those are just constants. So all I got to do is take that K to the 1/2 power and think about how would I find the derivative of that? Well, I would just use the power rule. So I'm going to bring that 1/2 out front, multiply it by what's already there, 1/2 being the 0.5. And then I'm going to take my K to 1 less power, so it'll be to the negative 1/2. And then multiplied by the L to the 1/2 because that doesn't change, it's just a constant. Now if it were plus L to the 1/2, it would go away, wouldn't it? Because it would be, the derivative of that term would be 0. But this stays because it's multiplied by the K term. Now to simplify this won't be too tough. The 400 divided by 2 is 200. The L to the 1/2 power stays in the numerator, but I'm going to move the K to the 1/2 power to the denominator. And the reason that I'm going to do that is because it's to a negative power. And anytime we have anything to a negative power, we would put it in the other position. And then likewise, the partial of Q with respect to L, now I'm going to have labor change, so I'm going to hold my capital constant. So that's the ceteris paribus part. And now I'm just going to change my labor by 1 unit, and I want to see how that would affect my output level. It's going to look really similar, but now I'm just going to have this be my variable, L to the 1/2 power, where the rest of the stuff that's here is just going to be held constant. So I'll bring down the 1/2 power, and that will give me 200. I'm just going to go ahead and write it as 200 now. We know it'll be 200, 1/2 times 400. The K to the 1/2 stays the same, but now it's going to be L to the negative 1/2. 1/2 minus 1 is negative 1/2. So I'm just going to go ahead and write it in the bottom. Now later in the semester, so we're done. We're done with the work we needed to do to find the partial derivatives. So this is done. But what we want to do eventually is we actually want to find the ratio of these two things. This one divided by this one will actually give us the slope of the firm's isoquant, which is it's called the marginal rate of technical substitution. So I don't want to mess you up too much with that, but let me just go ahead and show you how nice this ends up working out, and that because we're going to see this a lot with the utility functions as well. So the marginal rate of technical substitution is the partial of Q with respect to L, which we have already found is 200 times K to the 1/2 times L to the 1/2, divided by the partial of Q with respect to K, which is 200 times L to the 1/2 over k to the 1/2. And this is going to simplify so nicely, you guys. The 200s cancel each other out. The k to the, this is just going to end up being k divided by L. So even though it looks really nasty when we think about what we end up with up here as we go to take the derivatives, the final answer is going to be nice and compact and easy. And I'm not going to show you all the little steps there because I'm going to show you with the utility function that I'm about to do. It's a really nice and easy answer once you've got the simplification done. All right, hopefully that's helpful, and I will create another video that will show you the solutions to the extra practice problems with partial differentiation.